Boom. All right. Rotational kinetic energy. This is the last big part of rotational motion. So Ke sub r is equal to 1/2 I omega squared. Looks really similar to our last kinetic energy, 1/2 mv squared. So instead of having mass as your inertia, now you're dealing with your rotational inertia. And instead of having your straight line velocity squared, it's your rotational speed squared. So it's pretty much the same. Not much has changed, just the names of the variables, but the ideas behind them and why we use them in the places that we do is still the same. All right, let's look at two different problems here. Let's start with an easy one. What is the rotational kinetic energy of a hoop with a radius of 2 meters and a mass of 5 kilograms that's traveling at a speed of 20 radians per second? All right, so here's my hoop, and he has a radius of 2 meters, mass of 5 kilograms, traveling at this speed. So Ke sub r is equal to 1/2 I omega squared. So 1/2 I for the hoop is just mr squared. And my speed is given to me in terms of 20 radians per second. Pretty straightforward. So I'm just going to plug in the values that I know. 1/2, mass of 5 kilograms, radius of 2 meters. Don't forget to square the radius. And 20 radians per second. And that whole guy gets squared too. So you plug in all those values, and in the end you get 4,000 joules of rotational kinetic energy. And that's just his rotational kinetic energy. He also has linear kinetic energy due to his straight line linear speed. But right now we're just looking at this value in terms of his rotational kinetic energy. Well, let's look at a different problem where maybe not as many variables are given. Here we're trying to find the rotational kinetic energy of a solid disk. Has a mass of 2 kilograms and a radius of 0.5 meters and has a linear straight line speed of 4 meters per second as it's rolling on a flat surface. So here I'm not given omega, but I know that V is equal to R times omega. So omega equals V over R. So we got to keep that in mind as we look to solve this problem. We're going to start off the same way as we did before. Ke sub r is equal to 1/2 I omega squared. Now we're going to start inserting our values for I and W. Here we have a solid disk. Solid disk is 1/2 mr squared. So we're going to expand our formula. 1/2 mr squared. And for W, we said that it is V over R. So my straight line velocity is 4 meters per second, and my radius is 0.5 meters. So I'm just going to distribute this here, so I get V squared over R squared. And that's for my omega. Now, I have things that can start to cancel out. So look at the radius. Radius squared, gone. I'm just going to multiply these halves together, so it looks like 1/4 m v squared is what Ke is equal to in the end. All right, making things easy on us. So 1/4 of a 2 kilogram mass times the velocity of 4 meters per second. The velocity still gets squared. And when you put that all together, it's just 16 joules. Not a whole lot going on there. But it's just a different way that you can solve for rotational kinetic energy if you're not given rotational speed. So you just have to know V equals RW, and you can solve in a lot of different ways. All right, that's it for today.